Hi everyone, I'm Giacomo Fenzi, and today I'm here to give a talk about the Lossy Trapdoor Function based on the paper by Chris Pikert and Brent Waters in 2007. So first of all, I'm going to start by giving a motivation of why this paper is important and which problem it aims to solve. So in particular, in cryptography, there is a lot of relevance about primitives or basic tools that are used to build more complex tools such as cryptographic systems. And in particular, two of them which are particularly important for our issues are trapdoor functions and in the CCA-secure public key encryption schemes. So trapdoor function, in a sense, are functions which are easy to evaluate and hard to invert unless you have some access to some additional input, which essentially allows you to cheat a little bit and to get back for given an element from the image to get the corresponding element to the domain which was used to evaluate it. So they're using a lot of schemes. So for example, the textbook RSA scheme, which is very common and not very used, but very well known, is actually based on a trapdoor function, as we will see soon. And so they are a very basic building block for a lot of schemes. Unfortunately, despite that, they are also remarkably hard to instantiate. And in fact, before this paper, so in 2007, actually, it was actually released officially in 2009, the only techniques that we knew for constructing a trapdoor function were based on the hardness of integer factorization. While there are some other assumptions which are commonly used in many other topics, which were not known to give a trapdoor function. And in particular, in this paper, we're interested in the assumption related to the discrete logs, such as the decisional Diffie-Hellman assumption, and to those related to lattices. And the reason that we are interested in these instantiations is because, for example, problems on discrete logs can sometimes be more efficient than those based on integer factorization. And for lattices, instead, they are not more efficient, but they're often like the very desirable property that they have is that they are quantum resistant, which, of course, since we say that quantum computing might be coming at some point in the future, is something that we're trying to move towards. Similarly, indistinguishability under chosen ciphertext attack, or in CCA security for short, essentially says is the basic security requirement that we have for public key encryption scheme. And essentially, it says that the system remains secure even in the face of an active attacker. And despite this also being a very, very well used and well-known cryptography notion, the instantiation that we had were only from factoring and discrete log assumptions, but there weren't any for lattices. And these papers aim to solve this problem. How does it do that? So the paper does prove a lot of things. It actually is quite a long paper, but I suggest to read it because it's actually very enjoyable. And it solves the problem by introducing a new primitive, and those are lossy trapdoor functions. To give some intuitions, these are trapdoor functions which have two modes. In one of them, they're just trapdoor function in the usual sense, and in the other mode, instead, they actually lose some information. So it is actually information theoretically hard to get back to invert them. And the idea is that the switch between these two modes happens in a way that it is impossible to detect from an attacker. And that's the main building block. And then they show how to realize this lossy trapdoor function from a wide variety of cryptosystems. In particular, they show construction from factoring, from the discrete log based assumptions, and from lattices, which in turn, from the net result, which is the lossy trapdoor function imply trapdoor function, give the first known construction of trapdoor function from these assumptions. The paper then goes very further in depth, and he creates black box construction of a variety of cryptosystems. In particular, he shows how to use this lossy trapdoor function to build CCA-secure cryptosystems, and in particular, witness recovering. So this means that essentially the way that the system works is that for encrypting, it selects a piece of randomness, and then he obfuscates it in a way using the injective trapdoor function, and then to decrypt it, you will use the trapdoor to actually regain this piece of randomness and see that the encryption actually worked as it should have. It also shows a lot of other things. I have a nice summary at the end, but just to wet our toes a little bit, there are construction for collision-resistant as functions and for oblivious transfer protocols, which also have some good relevance in the field of secure multi-party computation. So to give a bit of clarity, this was the state of the art before this paper was published towards the connection that we knew from computational assumptions and their R security properties. And this paper goes to actually show this particular connection. So in particular, I just wanted to tell not to be too confused about all these ABO. These refer to all but one function, which is an abstraction over Lossy Trapdoor Function, which is actually equivalent. So, and we will show that we can use those to implement CCA security in a very nice way. So without any further ado, let's start into the meat of the paper. And first of all, we're going to be starting with defining trapdoor functions in the traditional sense. So informally, we say that a trapdoor function is some family of functions that it is easy to compute, but it is hard to invert unless you have access to some extra information, which is the trapdoor. We can, of course, make this formal, and we can say that a trapdoor function consists of three algorithms: S, which is a generation algorithm; F, which is an evaluation algorithm; and F to the -1, which is an inversion algorithm. So the idea is that as a functional requirement, we have that the generation takes a security parameter, and then it returns a function description S and a trapdoor T, which you can almost think as a public secret key pair. Now, given the function description, the evaluation algorithm will essentially compute an injective function. And in particular, there's a note to be made here about injectivity. There are generalization of trapdoor function which do not require injectivity. They just have that the trapdoor allows you to get one of the many possible inverses. But in our cases, it is actually injectivity, the notion that we really want, because, for example, for the CCA-secure scheme that we were going to be building, it is needed to be able to recover the randomness exactly. It is not so. In that sense, it is important that the inverse can actually be computed, and it is a function and not some sort of different mapping of sets. So that's the important thing, that it is an injective function, and its domain is 0, 1 to the n, where n is usually dependent on the security parameter. And then we have the inversion function behaves as it should do. So since S is an injective function, F-1 is the inverse. So it exists and it must be it. But to compute it, you actually need the trapdoor. And something which I would like to note is that we assume that the trapdoor kind of knows enough information to actually not need the function description. And that's just for convenience. We could actually extend this to actually take the function description as well and have shorter trapdoors, but for convenience, this is just the best way to do it. So these were the functional requirements. So now we have to talk about the hardness requirements. And the hardness requirement is similar to those for one-way function. It says that for any probabilistic polynomial time attacker, it will be hard to invert with non-negligible probability. So unless we have a trapdoor. So in this sense, you see that the attacker gets a security parameter, he gets a function description, and he gets an element from the image of the function. And we say that the success probability is the probability of outputting the X, which was evaluated in the domain. And we say that this is hard for all computational attackers. Now, to give an example, we have the very well-known textbook RSA. So again, I should warn you, do not use this in practice, especially if you're trying to use in CPA security. But for trapdoors, it is a very well used construction. So how does it do it? So the generation algorithm does everything that you do in normal RSA. So you select some primes, you compute a product of primes, you select some E, so such that it has an inverse modulo the Tottian function, which you can compute efficiently knowing P and Q. D is the inverse, and the public key are the same public keys that you have in RSA, so the modulo and the exponent. And the secret key, we save the public key that was related to the point I was making before, and we save this inverse. And the idea in our RSA is that an attacker which only has n will not be able to compute phi of n, and so it will actually be hard for it to, sorry, it should be capital N. It will be hard for him to actually invert properly. Sorry, to actually compute the secret key. And for evaluation, we do essentially what is RSA decryption. So we just evaluate the public key exponent modulo the modulo. And for decryption, we use the trapdoor to decrypt. And correctness follows exactly by the fact that E is the inverse of D, and the hardness to invert is almost exactly the RSA assumption. I'm sorry, I completely botched. It should have been a D. It should have been a D, and this should have been a capital N. I'll change it in the slide which I publish afterwards. But anyway, this is just an example which I wanted to make, and in particular, this is based on integer factorization, and there are other schemes which also are based on the same branch of problems, such for example at the pi cryptosystem, which does very similar things. In particular, the hardness to invert of this trapdoor function is almost exactly the RSA assumption. Now, for lossy trapdoors, as I said before, there's this idea that there are two modes. There is an injective mode and a lossy mode. And the way that we model this formally is by having the generation algorithm take an additional parameter which tells you which mode it is. So if to think about a practical thing, the generation algorithm will be run by, for example, the person which is publishing public key and secret key pair. And so you will decide, in a way, the adversary will not be able to tell whether it is chosen 0 and 1. That's the computation, the hardness assumption, essentially. When we're in an injective case, it is the function behaves functionally exactly the same as a trapdoor, and when we're in the lossy case, it loses information. So the way that we will see it is that it maps the domain to an image which is much smaller. So in particular, we can make all of this formal, and we say that a function is nk lossy. So n is the size of the input, and k is the lossiness, which is how much information the lossy function loses. And again, we will have the same triple of algorithms, so generation, evaluation, and inversion. Only that we will have that the generation algorithm takes an additional input, and I just define it like this for convenience, because otherwise it's hard to remember which one is which. And the idea is that the injective branch is functionally the same as a trapdoor. So you given a security parameter, it returns a function description and a trapdoor, and the evaluation function is an injective function, and you can invert with a trapdoor, exactly as in the trapdoor case. Instead, lossy will generate a function description and not a trapdoor, because in the lossy case, it is actually information theoretically hard to invert. So even with a trapdoor, it wouldn't be possible to it. So essentially the function s will the function s will be a function, but will not be an injective one. It will be one which maps 0, 1, n, which of course is size 2 to the n, to something with an image size of at most 2 n minus k. And this n minus k is what we call the residual leakage. And essentially, the smaller residual leakage is, the bigger k is, and so the more lossy you have. So these were the functional requirements, these two. And for the hardness one is that if we're given an S which comes from S injective, and if we're given a S which comes from S lossy, those are computationally indistinguishable. So any polynomially bounded attacker will not be able to tell it. And of course, something to note here is that an unbounded adversary might actually be able to, because essentially the only thing that you need to know is that if you can find a collision from the description by evaluating, then you will be able to actually figure out that you've been given a lossy function. Or even if you can actually brute force the trapdoor, and if it inverts successfully, then it is very likely that it is the injective one. So, but for us, we're just concerned with polynomially bounded attackers, and we say that it is impossible to efficiently tell them apart. Now, there are some subtleties with regards to the definition. And the first one is that it really relates to a collection of lossy trapdoor functions. And as I said before, this k is the lossiness of these family of functions. We call this n minus k r the residual leakage. We will see it a bit later. But the most important thing which I wanted to mention there really is no hardness requirement, at least no direct one, on inverting outputs of SJ. So as you can say, if we go in the trapdoor case, we have this hardness to invert assumption. Well, here we don't have it. We just functionally they behave the same, but the computational the hardness, it is hard. And in fact, we will see that we can see that it will be hard to invert thanks to the they're directly based on this computational indistinguishability. And this will be the proof that we will see in a couple of slides that the Lossy Trapdoor function imply trapdoor functions. Finally, there is also a note in this talk in particular, I will not be talking about the lattice part because it becomes complicated and messy, and honestly, the talk will become way too long. But I just wanted to note that if you're trying to do an instantiation with lattices, at least the one shown in the paper by Pygart and Waters actually does not satisfy the condition of Lossy Trapdoor function, at least not all of them, and not not in a very strict sense. The idea is that lattices are a bit weird, and so to actually, when you create the instantiation, you can only require that these functions hold with this requirement hold with overwhelming probability rather than unconditionally. And so this leads naturally to a definition of almost always lossy function, which you take this into account. And functionally, they behave very, very much the same, only that you have to account for this probability of them, for example, not being that injective or not being that lossy. And that's something that I just wanted to mention for completeness. Now we can introduce the second primitive that this paper introduces, and those are all but one trapdoor functions. And again, these are very, very similar to lossy trapdoor functions. The only very much different is that instead of sampling a single function, you sample a family of them, in which all of them are injective apart from one, which you select at the generation. So, and given the descriptions of this function, you will not be able to tell which is the lossy one and which is the injective one. And this turns very, very useful for our creation of the CCA-secure cryptosystem later on. So in particular, we still have the same API with the NK and the free triples, only that instead of taking a 0 and 1 input, the generation algorithm takes a branch, which is the lossy branch. And for any branch which is not the lossy one which was selected, the evaluation function can be evaluated on that branch or tag, whatever you want to call them, and it behaves injectively. Instead, if we evaluate the evaluation algorithm on the lossy branch, it is lossy in the sense that we defined before. And given any two different branches, it is hard to tell which one was chosen as the lossy one, computationally indistinguishably. So that's the idea of all but one, and they provide a good level of abstraction, which allows us to actually use them for CCA security in a very elegant way. And in fact, I have some extra slide afterwards which show that all but one function and Lossy Trapdoor function are actually equivalent. But yeah, you can check it on the slides. It's actually a very easy proof. Essentially, you show that all but one function and Lossy Trapdoor function are the same. If you only have two branches, and then you show that you can actually stretch the number of branches in all but one trapdoor function, but by reducing the lossiness appropriately. And you can check the details in the slide or in the paper if you so want to. So let us now show that the Lossy Trapdoor function actually imply trapdoor function, and this is actually quite easy to do. In particular, we have noted before that in the injective case, the Lossy Trapdoor function behave exactly as a trapdoor function. So we can see that for the completeness or the functional requirement, whatever you want to call them, the injective functions which are sampled by the injective generator of the Lossy Trapdoor function satisfy all the requirements. So they are easy to compute, and they can be inverted with a trapdoor. Now, the thing that we have to show, and that was the point I was making before, is that it is hard to invert in the case. And well, the way that we do that, we reduce this in a very classical way to the computational indistinguishability. So the note that we do is that if we are in the injective case, then it might be possible that there are adversaries which are, well, we will act by contradiction and we'll say that there is inverter which succeed non-negatively. While if we are in the lossy case, actually will be informationally theoretically hard to invert. And you can actually make this very, very formal by using entropy. I have some slides on that at the end, but I will just try to give the intuition here. So we do a classic reduction. So we suppose that A is some inverter for the function generated by S injective as a contradiction, and we build D, which is a distinguisher for the function description. So essentially, we're trying to say that if we have an inverter, this thing does not hold anymore. And we build this DA, which essentially behaves as following. It takes a function description as input, and it randomly samples an element of the domain. It evaluates the function description at that element, and it gives it to the inverter. Here, I've just dropped the security parameter because it just was a little bit nicer. And he asks the inverter to actually invert, and then he returns whether the inverter was right. And the idea is that if S is an injective one, then this inverter by assumption will succeed with non-negligible probability. Instead, if we're given something which is lossy, no inverter, not even one which is almighty and powerful, will actually be able to invert because they simply don't have enough information. And so in one branch, we will succeed with non-negligible probability, and in the other branch, we will succeed with the almost negligible probability. And since there is a disparity between the two branches, DA will actually be able to distinguish them, contradicting our assumption. And essentially, this shows the Lossy Trapdoor function actually implies Trapdoor function, which is a very, very nice result. And in particular, what I would like you to focus on is this paradigm on switching between lossy and injective. And this idea that you cannot distinguish them helps a lot immensely in the proof. And I think that's actually the most, as I was speaking with Professor Patterson before, it is possibly the most important thing that the paper conveys, this idea of being able to switch from something computationally, maybe computationally infeasible to something which is actually informationally theoretically infeasible, which in the context of game open proofs, they make them very, very easy, as we will see in the CCA case. Now, I would be remiss if I were to actually show you how beautiful Lossy Trapdoor functions are, how nice they are, if I weren't actually gonna give you ways to construct them. And in fact, I'm gonna give you some let's call them guidelines. I would like to say a framework, but it isn't actually a formal framework. These are some guidelines that Python and Water showed that are actually almost the only things needed to make a Lossy Trapdoor function from a cryptosystem. And in particular, you need three main properties. You need well, first of all, you need an encryption scheme, so it needs to be semantically secure, and then you need it to be additively homomorphic. Randomness needs to be easy to secure. Must be secure to reuse, and it must be isolated. And we'll see exactly what these things mean later on. And why do we need those? So essentially, the main idea is that additively homomorphicness allows us to evaluate matrix vector products in the encryption. So essentially, if you have an encrypted matrix, for example, and a non-encrypted vector, you can actually compute the matrix vector product, and you get the encryption of the matrix vector product without knowing what the matrix is, because it's still encrypted. So this is the idea, and we will show that we can encrypt for two very different matrices, like the identity matrix and the zero matrix, in an indistinguishable way. And since we can evaluate this matrix vector product, we will use that as the evaluation function for our scheme. Next, we want it to be secure to reuse randomness. So the idea is that even if we use the same randomness, but we use different keys, the scheme will not be broken. And this is it is good because essentially allows us to reuse randomness a lot, which helps with the lossiness. And that's the idea with it. And finally, we need the randomness to be isolated, so that essentially we can essentially pull out the randomness and it's not intertwined with messages or keys. And that's something that will be useful as well for the lossiness. We will be showing in the next slide a realization from the DDH assumption, but you can also do a very similar thing with lattices based on the learning with error problem, with again the difficulties and the caveats which I was talking about before. So to do that, to actually realize it from the decisional diffeasible problem, which again is a discrete log related assumption, we will consider the following variant of what's called the Al-Gamal cryptosystem. In particular, this variant encrypts a single bit, and I will not go too much into details, but it takes some randomness R, which is isolated in the sense that it is not dependent on the messages. And the thing which I wanted to mention mostly is that this discrete log that we're taking is not actually R to do, because if m is 0, 1, this expression here will actually only ever be the identity if m is equal to 0, or g if m is equal to 1. So this is actually very, very easy to solve. It's just very convenient to write it this way. And what's important about this scheme is that you can actually prove its security based on the Diffie-Hellman assumption, and in particular, it is additively homomorphic. So I've used these funny symbols to denote component-wise multiplication, and it's just component-wise exponentiation. And the idea is that if we're given two encryptions of two different things with two different randomness, doing component-wise multiplication gives you an encryption of the sum of the messages and the randomness. And with exponentiation, it gives you a multiplication. And this actually does not hold only for m in 0 and 1, but it holds for all elements of ZP. So this is something which actually comes almost directly from the complete Al-Gamal scheme. But since in this paper we only need to encrypt and decrypt 0 and 1, this is a more convenient way to do it. And in particular, I also wanted to mention that homomorphicness is a very good property for our case, but in other cases it actually isn't. So, for example, when you're working with I don't know, signatures, or when you're working with some particular notions of that sort, such as max and all of that, malleability is actually a property which we do not desire, because that allows the message to the adversary to pass related messages to the adversary and win some of the and break some of the security notions that we require. But it is very cool. I like it a lot, just from an abstract mathematical perspective. And in our case, it allows us to do a lot of very cool stuff. So without any further ado, we will show how to encrypt a matrix, and we do that in a very natural way, I would say. So essentially what you do, you select n public key secret key pairs and n pieces of randomness. And you encrypt the matrix in a way that in the same row you use the same randomness, and in the same column you use the same public key. So no public key randomness pair will ever be reused. And that's and since we assumed before that the scheme is as secure to use randomness with different public key, this still gives you security. And you can prove this formally via some n-squared hybrid games. And in fact, we don't even need to decrypt. We're just gonna be talking about this operation of encrypting in this way as a matrix encryption of Zm for Z some private keys. And yeah, so essentially we will be seeing that in the next slide, there will be our scheme will use two encrypted matrices. We'll be using one encrypted matrix as the function description for the Lossy Trapdoor function. And the idea is that we can actually switch between one and the other, and the adversary will not be able to tell, because this scheme is secure. This matrix encryption is undistinguishable. So the scheme is actually very, very simple in a certain sense. So what you do in both cases, you select a suitable group, you select an array of private keys, and you encrypt under these private keys the identity matrix in the injective case and the zero matrix in the lossy case. And you then return the encrypted matrix as the matrix description. And in the injective case, you use the private key as a trapdoor. While in the lossy case, of course, you cannot have a trapdoor. And as I was saying before, evaluation is just computing. So you take the input, which will be an n-bit string, and you interpret it as a row vector. So essentially, you interpret it as a row vector of length n, whose entries are all 0 and 1. And you essentially compute this vector matrix product using the homomorphic property, and then you return this is essentially the encryption of doing X with the matrix that we had encrypted here. And to decrypt, you just simply do it component-wise. So you given a vector, that's an encrypted vector, you just decrypt using the trapdoor that we have stored here component-wise. Why does this work? Well, I don't care too much about the group generation. It's important to say how hard the Diffie-Hellman is, but not for much else. But essentially, that means when you do this matrix vector product using the homomorphic property, you will see that the jth element of the encryption actually is the encryption which with the jth public key of the jth row with some randomness, which only depends on RNF. So essentially, if you go through the algebra, and I suggest you do the 2x2 case, because if you go bigger, I don't like doing matrix multiplication that much. But essentially, you will see that these are only is the scalar product of R and S. So it only depends on that, and it does not depend, for example, on the matrix that we have encrypted. And in particular, you can see that here, if we replace the two matrices, you'll see if M is equal to IN, you will see that Yj is just the encryption of the message under this randomness. So you can actually decrypt very efficiently. Well, if M is the odd zero matrix, this will just be an encryption of 0 under this randomness. So we don't. One of the reasons why we don't even need a trapdoor is if we are in a lossy case, we already know that this will be an encryption of 0, and we actually don't need to decrypt in that case at all. Now, this is the scheme. It looks quite simple, and there are we now just to check that it is actually a lossy trapdoor function in general. And in particular, we will be showing that this construction is n minus log p lossy. So if you look about this three algorithm, all of them are clearly probabilistic polynomial time. Since in the injective case we can decrypt, as I was showing before, then the evaluation actually evaluates an injective function. So that's the injectivity conditions are met. Now for the hardness actually follows very easily just from since we have shown that the matrix encryption actually is undistinguishable, then also the function description will be undistinguishable. So we get it almost for free from the fact that Delgamau is a secure encryption scheme. And finally, we just have to show that the scheme is lossy enough. And the idea is that in the lossy case, we are only ever encrypting 0 with some value R. And this R depends on heads and the input randomness, but this R can take at most p values because it is an element of ZP. So essentially, since this is the only thing which can really vary, the residual leakage must be at most log p, and so the loss must be greater than n minus log p. So that's the rationale for it. Okay, now that I've shown you how to make a lossy trapdoor function, we can use to finally prove something which I feel is very cool, and that is CCA security. In particular, we're talking about the notion of indistinguishability under chosen ciphertext stack for a public key encryption scheme. So to do so, we will need some primitives which help us, and in particular, we will require a strongly unforgeable one-time signature scheme, NK lossy trapdoor function, and an NK prime all but one trapdoor function, plus a collection of pairwise independent hash function. And I would like to note here that all of these, these three actually reduce to lossy trapdoor function, while pairwise independent hash function can be made from actually different assumptions. So for example, there is one idea in which you take the matrix product and you shift it by some private key, and that's one way of getting pairwise independent hash function. But I digress. Essentially, for the strongly unforgeable one-time signature scheme, something that you might want to do, and it is very much not efficient, is use lossy trapdoor function to get trapdoor functions, which also in turn imply one-way function, which also in turn imply strongly unforgeable one-time signature schemes via Lamport construction, for example. There are some other technical things which I would like to mention. The message space, we actually only encrypt messages of a fixed size. And in particular, the signatures must be in a space which is compatible with the branch space of the all but one, because essentially we will see in the security proof, we will make so that the lossy branch becomes the signature branch. And essentially this allows us to lose information in the left or right oracle case. You also have some requirement of on K and K prime. They need to be relating in a certain sense, but I don't want to talk too much about it. But just refer to the paper if you want to instantiate this in practice. And don't in general, because it's not that efficient of a construction. There are better choices, I think. And the construction, though, is very, very elegant. So again, as an encryption scheme, you have a generation, an encryption, and a decryption step. So for the encryption, you essentially sample an injective lossy trapdoor function and an all but one function whose lossy branch you select to be 0. You also select one of as function from the family of pairwise independent ones. And as public keys, you give the function description and the hash function. And as secret key, you just give the trapdoors. And in fact, we won't even need to use the trapdoor from the all but one function, but we keep it in there because we will see we actually will need it in the security proof. But for us, for encryption, we will essentially generate a verification and a secret key from the signature scheme. We will generate a random piece input. This is, as I said before, related to the notion of witness recovering. So we select some randomness, which we then encrypt, essentially obfuscate, and which we will then recover to decrypt. So essentially we select this randomness, and then we evaluate the lossy trapdoor function and the all but one function with the public keys or with the function description at this point. And in particular, with the all but one function, the branch that we selected to evaluate is the verification key that we have just selected. And now for the main meat of the scheme, we take the message and we take the randomness and we use the pairwise independent hash function to essentially turn it into a stream of random bits. And we encrypt in a one-time pad manner. So then we sign all our pieces of information to ensure that the adversary cannot tamper with it too much. And then we just return these 4 pieces of information. Oh, sorry, this is supposed to be the sigma, not omega. I apologize. I must have skipped. I'll change that in the slides as well. As for decryption, you take a secret key and a ciphertext. First, you verify that the signature that you've gotten, so this signature here, is correct. And if not, you just simply return that the decryption failed. Then you use the trapdoor of the Lossy Trapdoor function to recover the randomness. You check the C1 and C2 are as they should be, which essentially does another level of verification. And finally, you use this randomness to recover this age of X, and you use that to decrypt the message. So first of all, I wanted to talk about the CCA game and the reason why it changes a bit from the CPA game. So with Lossy Trapdoor function, it is very, very easy to implement CPA security. And essentially, the idea is you do something extremely similar, and then you switch from, you don't even need the all but one function, and you switch from an injective to a lossy mode indistinguishably. And the adversary will not be able to tell at all. And for the CCA security, you would think you would be able to do something extremely similar, but since in the CCA game, you actually have access to a decryption oracle, if you simply do it naively, then you won't be able to decrypt the query that the adversary gives you. And the adversary will be able to tell that you switched. So in that sense, we are not, the trivial construction does not work in CCA security. And that's why we need to have a bit more different things to do. So anyways, that's why we have this construction, this double lossy and all but one kind of scheme. So first, let us recall though what the CCA security game is. And essentially, you have the adversary has access to a setup, which essentially samples a bit which is kept hidden from the adversary, and he returns the adversary this public key. Then it has access to an encryption oracle, which is really a left or right oracle. And the idea is that the challenger will encrypt either the first or the second message that the adversary gives based on what bit was selected, and it will be just returning that. And finally, you have a decryption oracle, which given a ciphertext, if it is not one of those which was queried by the left or right oracle, it will just he'll decrypt it and give it to the adversary. Otherwise, it will just say the decryption has failed. And The attacker wins if after all this interaction, it is able to guess correctly which which B was actually used. So if the encryption that he got was actually of the left or the right message. So in particular, this is in particular in this paper we act with a slightly modified model in which the adversary is only ever allowed one encryption oracle query. And while this seems very restrictive, it can actually be shown that the multiple query and the single query model are equivalent. And this allows us to do a nicer proof, one which actually fits on one slide, which is nice. So without any further ado, here are the proof. The proof is a game hopping proof in the traditional sense. And we first do a little change, which is based on the fact that we only ever do one encryption. Since we only do one encryption, we can essentially move the generation of the verification key secret key pair in the setup rather than in the encryption one. And the adversary will not change. The game is exactly the same. It behaves functionally the same. But this essentially allows us to cheat a little bit and to do some other changes in setup, which allows us to actually switch the game. So the games are as following. The first, G1, is the original CCA security game. In G2, you essentially make it so that in the decryption oracle, if the verification key that the adversary sends in the challenge ciphertext is equal to the verification key that we have sampled in setup, we just return bottom. And the idea is that the only case in which this happens and the adversary would have received something different from bottom is when the adversary actually managed to do a forgery of the signature. So this switch can actually be reduced to the strong enforceability of the signature scheme that we're using. So we can do this switch very efficiently. So based on this notion. Now from G2 to G3, we change the lossy branch of the all but one trapdoor function to be the verification key that we sampled in the setup. That's one of the reasons why we move it there. And again, this switch can follows directly by the computational indistinguishability of all but one trapdoor function. So that's the main idea. In G4, you do a very small functional change. So if you go back here, we were recovering X using the trapdoor of F. Now we do the same, but we use the trapdoor of G. And we can do that actually. This does not change at all what the adversary see because of the correctness of both schemes. So it is completely fine to do it. And that's the way that we actually ensure that at all points in time the challenger can always decrypt everything else. And finally, for G5, we essentially replace the injective function with a lossy one. And this is also follows directly by the computational indistinguishability of the Lossy Trapdoor function. And in the final game, we can actually show that the adversary actually has no chance of winning. And the idea is that when he gets his encryption challenge, both the F and G will be evaluated as lossy branches. And since they're evaluated as lossy branches, the things which he returns, so all the various C1, C2, and C3 will actually leak no information whatsoever about the randomness. And so based on the pairwise independence and based on the one-time path security, in G5, not even an unbounded attacker will have any success. So that's the argument. And since all these steps can be bounded by negligible probability based on some computational assumptions, and the last step is actually negligible success probability, by this sequence of games, we have shown that the scheme is actually CCA-secure. So this is actually very nice, and compared to a lot of the other CCA proofs which I've seen, it is actually incredibly clean, especially because he only does it in pretty much a black box manner. It is not as efficient as other reduction, but it is very, very nice. So, as I said at the start, this paper was very, very long. Like, it it took me a while to go through it, and there were a lot of things which I actually do not have time to show at all. In particular, there was the equivalence of all but one function and Lossy Trapdoor functions. There were more efficient all but one construction from, for example, DDH. Essentially, the idea of that is that you still encrypted zero matrix for the lossy branch, but for the injective branch, you encrypt different matrices which are still in some way invertible and decryptable. And so there are a lot of other things which you can show, but I suggest you refer to the paper mostly for those, because otherwise this talk would be extremely long. Finally, there's a lot of related work in this field, and in particular, a lot of it is in the context of selective opening security. But first, let me just talk about a bit of the other things. So in there are more construction of Lossy Trapdoor functions, because the ones shown in this paper are not as efficient. So there are more efficient lattices one, there are more efficient one based on the decisional composite residue problem. There are more efficient k-linear based one. There are new ones based on quadratic residues. So there are a lot of other construction which improve the paper, and some of them argue that they are even simpler, but so they essentially improve the efficiency of the construction shown in the paper. Then there are some research on fields like lossy encryptions, in which essentially you have encryption schemes in which you have an injective mode in which you can decrypt, and a lossy mode in which actually the ciphertexts are independent from the plain text which they encrypt. And that's something which has been studied by Bellar and O'Fines. Then there are a lot of generalizations of all but one trapdoor function, and those are the ones which are mainly in the field of selective opening. And to give the rationale for this, the idea is that in CCA security we were very lucky, because the multi-query case reduces to the single query case. So essentially, all but being able to just informationally hide only a single message is enough for our schemes. But in selective opening, those are schemes in which the adversary is able to corrupt arbitrarily many messages and get not only a decryption, but also the randomness which was used for encryption. And it is a very strong notion of security. And in particular, we will, in particular, that means that on all but one function is not enough, because you may need to actually replace a big number of ciphertexts or encryptions. And that's why there's been this generalization based, which are all but n Lossy Trapdoor function and all but main Lossy Trapdoor function. And they both allow you to have many lossy branches, but the main difference is that all but n Lossy Trapdoor function, you select at the start how many branches you want lossy and which exactly they are. And those will be stored in the function description in a certain sense. While all but many, they allow you to sample it on the fly. So the function you've given will have lossy branches, which are hard to find unless you have a trapdoor. And if you have a trapdoor, you can actually find them and use them. And essentially, this allows you to have more efficient schemes, which have a better space complexity, for example. Other than that, there are other uses for it. For example, there's a generalization of a Lossy Trapdoor function in the field of identity-based encryption, which essentially is an encryption in which an identity is also associated with a public key. And also there are some schemes based on deterministic encryption, which is essentially a weaker notion in a certain sense, because randomizing, well, it's not a weaker notion, it's just a different notion. You can essentially use Lossy Trapdoor function to solve that problem as well. So in summary, I think the Lossy Trapdoor function are a very, very exciting topic, one which I've spent a lot of time researching and which I actually truly enjoyed studying and actually giving this talk. And in particular, I think that the most important contribution that they give is just this ability to do very elegant game of proofs, which I think is something very, very, very cool. Like in a sense, it is similar to how category theory enabled, in a certain sense, mathematics to get canonical proofs and very very beautiful proofs in a certain sense. So in the sense, I think Lossy Trapdoor Function allow you to get these plugged in, and they are very, very nice for actually doing this particular kind of proof, which to me is very, very interesting. So I hope you enjoyed the talk, and well, I'll see you some other time. Thank you.